you should be able to model the dynamics of the coin toss. Like generally we assume the coin to be a rigid body, which is a reasonable consideration I will say, and with that you can do that. And in fact, you can show that it's not random. There has been studies that have showed that you can precisely control it given these factors. But we say coin tossing is random. So I am saying coin tossing is not random. Because you can always model the dynamics using mechanics. You can control the force, the rotation will be a function of the force you are providing and the initial condition. And air friction you can bring in, and that's the modeling part. So there is nothing randomness there. But we say that coin tossing is random. Because we do not know, or rather we do not model. We can know the air friction and all those things with precise accuracy, but we are not modeling it. And also you will realize that when coin is tossed, generally it is like this. So the initial condition is hidden. If the initial condition is not known, then that changes everything. Also, the force we cannot exactly predict how much force someone is giving, which means randomness stems from our lack of knowledge. Lack of knowledge can be because of I don't know the initial condition, I do not know the let us say the physics exactly. Even if I know the physics, I might not be able to solve the physics exactly, and you can come up with other conditions also. There will be factors probably that which we are not considering and all those things, right. So what I was saying is that coin tossing is actually a function of initial condition, which is the initial state, what is at the top, what is at the bottom. Then it is a function of the force that we are providing, the air friction or air resistance, right. And what else is there? I will say these are the only things, and obviously the mechanics and dynamics you have to solve, so that is there. But the problem is that many of these things we are either not modeling or is unknown to us. And so the claim is that randomness stems from our lack of knowledge. Okay, and it's a philosophical discussion, and you can always argue in favor of that. For example, to my knowledge, the only thing that we can say is completely random is probably quantum experiments, right? The slit example where the light is going, it can either be particle or wave, and the outcome of anything in quantum we say is random. And it is proved that it is random. The same experiment you do in the exact same condition, you get different result. So that is the only thing that is completely random, probably to my knowledge. But I can always argue that probably there is a model which can exactly define it, which is not yet invented.
Sir, is it always random or is it different from the expectation, like double slit experiment?
Yeah.
Is it also, you would say that, is it a random event or?
It is a random event. So outcome is, if you have to model it, the outcome is probabilistic. You will not get the same thing again and again. Okay. And that's why these quantum computers and all those things is based on qubits, and they use this duality, which is it is neither dead nor alive if we take that example of cat, or 0 or 1 at the same time, and that's why it has lot of memory, because it goes in 2 to the power. So 3 qubit is 8 memory, so 2 to the power 3 in that sense, because it is happening both at the same time. Okay. So that is the idea. So yeah, we can always argue that nothing is random, and nothing will be random if you give me that the assurance that I know everything, and that will never happen. At least I don't see it happening, and therefore everything will always be random. Okay. So now we talked about probability definition, all of you know about it. We talked about event. Okay. So in a coin tossing example, the event is head and tail. Okay. So, in coin tossing, the event can be either head or tail. Okay. And when you take all possible outcome of an experiment, that is known as sample space. So, sample space is all possible outcome of an experiment. So, if you are tossing a coin one time, the outcome will be either head or tail. So, then the sample space is head comma tail. So, sample space is all possible outcomes of an experiment, which is obviously random. So, if you have to write it, S for coin tossing example will be head and tail, single turn, I am tossing it once. Okay. So, these are things you already know, okay. There is nothing new here, just doing a quick review. And now, with this, we need to proceed and try to define things mathematically in a little bit. Okay, I am not going to more mathematics today, but yeah. So, for example, when I write probability of event, I will write it as probability A is the experiment and it can take a value which will be either in this case head or tail. So, or in a general case I can write it in this manner. So, this means A is the event which is taking the value small a. So, small a we will call it as the realization of a random event, outcome of one experiment, and A is the general event. Okay. I am not yet defining any variable or things like that, but that is what it is. Okay. So, probability of A, as I said, I am now removing the equal to A for basically for compressed and representation. So, this is probability of A, okay, and I am not writing A taking some value, but it is probability of A taking some value. Okay. And now there are two terms that I will like to introduce. One is the joint probability and the other one is the conditional probability. Okay. What is joint probability? It is not necessary that you will always deal with one random event. You might be dealing with n number of random events. So, as long as you are dealing with more than one number of random events, you represent it using joint probability. For example, I have two coins. I am tossing two coins. Then the outcome can be head head, head tail, tail head, tail tail. So, this thing that I said is the joint probability, let us say, of event A and B, where event A is tossing the coin number 1, event B is tossing coin number 2. So, first let us talk about joint probability. This is probability that two events occur simultaneously. Okay. So, joint probability is probability of that two events occur simultaneously, and this is represented as probability, let us say A is equal to small a, B is equal to small b, okay, where capital A is the first event A, this is event B, and this is just I am taking two events. You can take n number of events, where n can take any value, there is no stopping on the number of n, but for simplification this is how we write it. Now, this I will represent as There are three ways of representing it. Either I will represent it like this. This is the one I will mostly use. This means joint probability of A and B. Or you can also represent it, and I might sometime do that, as probability A comma B, or you can write it as probability of A intersection B. Okay. I think the last one is probably the most common one, intersection notation. I mean, if you have to be mathematically precise, that is the one, but we want to reduce our effort, so I will use AB, no comma, no nothing. Okay. So, yeah. Okay. So, this is how joint probability is represented. So, taking the head and tail examples, let us say A is outcome of tossing coin 1. Okay. So, I have two coins, I will call it coin 1 and coin 2. B is what? Outcome of tossing coin 2. Okay. And we know in this case it is head and tail. So, how will I represent it? As a table. You can think of it as a 2D table, because it is 2 dimensional, it is easy. Okay. So, you can think of it as a table, let us say something like this. This will be, okay, let me make a box out of it. Okay. And then let us say this is A equal to head, this is A equal to tail, this is B equal to head, this is B equal to tail. Okay. So, that means what will be the entry in the first box? It is head head. That means coin 1 also I have obtained head, coin 2 also I have obtained head, right. The second one is head tail, tail head, tail tail. Okay. This is not the joint probability, this is just the event. If I have to write the joint probability, then it will be 1 by 4, 1 by 4, 1 by 4, 1 by 4, right. So, if I have to write the joint probability, I will just erase it and I will write it as, yeah, I will write it as 1 by 4, 1 by 4, 1 by 4, 1 by 4, and I am making an assumption here that the coins are unbiased, that is why I am getting that half and all those things, but let us write those numbers. Okay. So, that is the assumption, I mean it may not hold, but that is fine, I think. Okay. So, this table is known as joint probability table. Okay. The other thing I want to discuss is the conditional probability, and then I will go to the probability rules. Okay. Conditional probability is that what is the probability of an event given you have already observed the outcome of the second event. Okay. So, conditional probability is probability of observing or probability of an event, let us say an event A given B has already occurred. Okay. So, the name itself says there is some condition now we are putting. So, I am like asking that, okay, I woke up, I saw that the grasses are wet. So, what is the probability that it has rained? So, that is a conditional probability. My observation is that grass is wet. So, that becomes B. What is the probability it had rain at night? That is A. Okay. That is the example. And this is represented as probability A equal to A given B equal to B, but I will represent it as probability A given B. Okay. So, this vertical line is given. Okay. That is saying that whatever is on the right hand side of that vertical line has already occurred. Now, when I say something has already occurred, that means that is observed, that means that is deterministic because we have already observed it. Okay. Now, this is very important in machine learning because in machine learning you will always observe some data and you will like to infer something from that data. You will like to predict something from that data. So, from machine learning point of view, this B often will be our data set and A will be something that we want to infer from the data. A simple example, not machine learning, but let us say, so I want to find out what is the probability of getting a head, the same example last time, right. So, that in that case probability of head mu, that will become A. Mu is the probability of getting head. So, I like to find out probability of mu given I might have performed 10 experiments and I might have observed head, head, tail, tail, head, tails, I do not know, some data, and from there I will like to infer. So, we will go to that in more details, but this has relevance with, this will be heavily used in machine learning. That is all I will like you to remember for now. Okay, for now I only want you to remember that this will be heavily used in machine learning throughout this course in machine learning. Okay. So, that is all you need to remember for now. Now, we have defined the joint probability, which is probability of AB, and the conditional probability, which is A given B, or B given A can also be there, depends. If it is B given A, we will assume that A has already occurred, so we have observed it and now you want to infer about B. Okay. So, now with that setup, how can we relate these two things, the joint probability and the conditional probability? How can these two be related? And that brings me or brings us to the two most important thing that you will see in every lecture of this course, and you will it will be repeated to the extent that you will find it boring, but when you will give you a problem on that you will realize that it is not so easy. But these two things are the probability law. One is the sum law of probability and other is the product law of probability. And whatever we do in this course, it will always be about application of those two probability. It will always be. Okay. So, we have probability rules and we have two rules, sum rule and product rule. Okay. So, first what is the sum law or sum rule of probability? Okay. And remember that till now I am only doing it two variables, we will soon generalize it to n number of variables, but for I am taking a bottom up approach. So, we will start with two and then generalize it rather than taking a generalized and then bringing it down. So, yeah, sum rule is that probability of A is equal to summation over B probability of AB. Okay. And I will show it to you with an example how it holds, but if I have to write it in more specific or more detailed manner, it is more like A is equal to summation probability A equal to A comma B, and you will do a summation over B. So, that means all the possible values that B can take. Okay. So, when I write the summation over B, I do not write B equal to B. So, it is not a given value, it is all possible values of B, and you have to do a summation over that. Okay. And this is very easy to understand from the example we here, right. So, what was this example? Tossing of two coins. Now, what is the probability of head for an unbiased coin? Half, we know that. Now, look at it. What I am saying is I want to find out probability of A equal to head. Then what should I do? I should do a summation over B, B equal to head and B equal to tail. 1 plus 4 plus 1 plus 1 by 4 is equal to 1 by 2. So, for example, if I take this example itself, so in the previous example, probability A equal to head will be equal to probability A equal to head comma B equal to head plus probability A equal to head comma B equal to tail, which ultimately will give you half, and we know it is supposed to be half. So, what is expected is what we are getting. Okay. So, this is the sum rule. Okay. The other one is the product rule. Product rule, and this is basically giving you probability of AB, so the joint distribution is equal to probability of A multiplied by probability of B given A, which is equal to probability of B probability of A given B. Again, something you are aware of, right? Nothing that you don't know, quite obvious actually. Okay. Yeah. I don't think I am going to prove it, but you can easily prove it. If I go back to this example, let us say. So, again, like prove through example. If I ask you what is the probability that B will be equal to A will be equal to head, given B, I know that B is equal to head. What is the probability that A will be equal to head, given I already know that B is equal to head? Half, right? And how do you get it? See, probability A equal to head and B equal to head is equal to 1 by 4 divided by probability B equal to head, which is equal to half. 1 by 4 by half is equal to half. Okay. So, you can directly get it from there. Okay. So, just let me write down the example. Probability A equal to head given B equal to head is equal to probability of A equal, what happened? A equal to head comma B equal to head given by probability B equal to head, which is what, 1 by 4 divided by 1 by 2 is equal to half, which is what we know the answer, right? Any doubt until now? Should not be. I am just repeating what most of you or all of you probably know, right? Now, let us generalize. Okay? Let us generalize the sum law and the product law. So, generalization to n variables. Okay. The sum law, okay, let me see how should I generalize. So, let us say I want to find out probability of x1, okay, and I have been given probability of x1, x2, I said n variables, so xn. So, I know the right hand side, I want to find out the left hand side. How can I do it? Using sum law. What will the sum law look like? X1, summation over x2 to xn. So, n minus 1 summations I should have. So, summation, and this is n minus 1 summations. So, let us say this is over xn, xn minus 1, and the last one is x2. Okay. Yeah. So, this means that given that I have the joint distribution, joint probability, I can find out the individual probability just by doing a certain number of summations. Okay. That is what it means. And when you do this operation, it has a name. There are two names actually. One of the name is that marginalization. So it is said that I am marginalizing out x2 to xn, because what does marginalization mean? That I am ignoring kind of, right? I am not talking about them. So because I am doing a summation over them, on the left hand side they do not appear. So that is why this is known as marginalization. Okay. So this is known as, this operation is known as marginalization. And the distribution I got is known as, is called the marginal distribution of x1. So this is known as marginal probability in this case, not distribution. I have not yet come to distribution. So marginal probability of x1. So that is the terminology. So this is the marginal probability. There is another name that is used in place of marginalization, which is known as integrating out the variables. The name integrating out comes because you will see that this summation for continuous variable, when I go there, will become integration. And it will be like you are integrating out the variables so that those variables do not appear on the left hand side. So another common terminology is that integrating out. Okay, same thing, marginalization and integrating out. Okay. So this is the generalization of some law of probability for n variables. The other is generalization for the product law. So the generalization of product law is, again n variables I will take. So probability of x1, x2, now I am using the comma notation as you can see, xn, this will be equal to probability of x1, probability of x2 given x1, probability of x3 given x2 and x1, dot 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 probability of xn given x1 to n minus 1. Okay. So that means x1, x2 up to xn minus 1. So this is the generalization of the product law. Now I started with x1, you can start with xn, the law remains the same. Okay. And if you want to understand how do you generalize it, the idea is simple. When you are dealing with x1, consider x2 to xn as a composite event and call it B, and keep on doing that and you will reach this relation. Okay. So this is the generalization of the product rule for n number of variables. Okay. Now we will come to a very important concept again in the context of machine learning, which is independence of event. Independence of event is probably the most exploited thing along with the sum and product law for machine learning. You realize that we often assume things to be independent even when they are not, because that makes our life easier, and we will talk about that, how it makes our life easier. Okay. So statistical independence. So let us define it again in terms of two variables, but it can have more number of variables. Okay. So A and B are said to be statistically independent if occurrence of one does not affect the other. Okay. That is probably the dictionary definition of independence. You and me are independent if whatever you are doing, I don't care about that, right? I mean, my action will not be controlled by what you are doing. Then we are independent, right? In that sense. But then we are talking about statistically. And when we are talking about statistically, when I say that does not affect the other, now affect the other is a very vague term. Effect in what sense? Obviously it will be in the probabilistic sense, because we are talking about probability and statistics. So what should be the equation look like for this one? From this definition, can you write down, tell me this definition, can you write it mathematically? Exactly. PA given B equal to PA, because whether B has occurred or not, probability of A should not change. Probability of A given B is equal to PA and probability of B given A is equal to PB. What is happening? Okay. Probability of B given A is equal to PB. Okay. But these are not the definitions that we use at least when we are solving problems. Like if I give you two events and I ask you that examine whether these two events are independent or not, what do you use? Probability of AB is equal to probability of A multiplied by probability of B. That is the one that you generally use, which is a byproduct of this. This is the actual definition, and the byproduct of this is probability of AB is equal to probability of A multiplied by probability of B. And you can clearly say that this is, you are obtaining this from that definition only, because the product rule tells us that if there is nothing, then it should be A, this should be B given A, and because of independence B given A becomes B. Okay. So if there is no condition, the product rule was saying what? AB is equal to A multiplied by B given A, and B given A is equal to B because it is independent. So this is basically a byproduct of the definition. Definition is actually on the left hand side, the right hand side is the byproduct, but that is the one we use because we hate conditional probability, probably, I don't know, or some, generally we will not have access to conditional probability, if I may say so. Okay. So this is the independence. Okay. Now again you can generalize it to n number of variables, and that will give you probability of x1, x2, xn is equal to probability of x1, probability of x2, probability of xn, and you can write it, I mean, let me be little bit more mathematical, I equal to 1 to n probability of xi. Okay. Pi means product. Okay. So I am slowly introducing these notations because throughout this course we will heavily use such notations, because it will not be possible to write in the expanded form. Okay. So you will realize that. So this is the statistical independence for n number of. Okay. There is also a term which is pairwise independent. Remember that pairwise independent is different from mutually independent. Pairwise means you will take two variables and check that they are independent or not. So it is possible that things are pairwise independent but not mutually independent. Okay. Now this is one question we often ask actually in MTech interview of SKY. Very simple question actually, but people often get confused. Let's see. So suppose I am tossing a coin, right? The outcome is head and tail, right? So are these two independent or not? We are tossing a coin, the outcome can be either head or tail. So are these two outcomes independent or not? Head and tail. How many things they are independent? 1, 2, 3, 4, 5, 6.
How many times you are tossing the
Once.
They are not independent.
Okay, and how many things how many people think they are not independent? Again, same number of numbers, the others are confused. They are not independent because see, you are tossing a coin, right? If you get a tail, then it cannot be head, that probability is becoming 0. So by observing that you have got tail, that is actually telling us something about head, that you cannot get head. So these are actually mutually exclusive event, and mutually exclusive events cannot be independent, because mutually exclusive means occurring of once means that other will not occur. So that means that is giving you some information that other will not occur. Not occur is a very strong information. I mean, remember that generally we never get probability equal to 0 and 1. We only get it for deterministic event. So for mutually exclusive, it is actually making it deterministic. So it is such a strong information that you have. Okay, and this is a common confusion actually, because people confuse between mutually exclusive and independence. Okay, so this was independence. There is something known as conditional independence. Okay. So conditional independence is, obviously it has to do something with conditional distribution. So conditional independence is, given that I have event C has occurred, occurrence of A and B are independent. If that is the case, then we call it conditionally independent. Okay. So see, given C, which is an event, I am just using names, has occurred given that C has occurred, if occurrence of A is not influenced by occurrence of B, then A and B are conditionally independent given C. Okay. So that means given that C has occurred, knowing B has occurred will not give me any additional information about A occurring or not. Okay. So this means mathematically it is probability of A given B comma C is equal to probability of A given B, A given C. C, probability of B given A comma C is equal to probability of B given C, but probability of A given B is not equal to probability of A, and probability of B given A again is not equal to probability of B. Okay. And this can easily happen. Just take example of 3 friends. Okay. So let us say 3 friends, and we want to know that whether they will go for a tour or not, okay, during these summer breaks. Now we know that if friend B goes, A will definitely go, or if friend C goes, A will definitely go. Okay. And if friend B goes, then A might go or might not go. Now given that C is not going, then we know that A will not go. Whether B is going or not going, that becomes independent. Probability of A given that part will become 0. So there are many cases like that where, and this assumptions are used in many examples in machine learning. For such example, one of that is Markov chain. In Markov chain, we assume that whatever has happened just before is the only thing that is controlling. The past does not matter. So there is a whole area of probabilistic graphical model which is based on this conditional independence. Okay. And you should not confuse between independence, correlation actually, not independence, and causality, which I will talk later, but there is a sense of causality there that also comes with probability. but correlation probability, because people are often relate uncorrelated with independence, which is not correct. Okay. Okay.
Are these conditions always true, like when the events are
The right hand side you are saying, right? So it is
maybe
no. What I am saying is if two events, if A and B are conditionally independent given C, and only if that is the case, then this has to be true. Otherwise, it can be independent and conditionally independent. It is not only conditionally independent. So, for example, if I remove this equation, then it is possible for A and B to be independent and conditionally independent.
so
This is I want to enforce only conditional independence,
and
not the independent mutual, the unconditional independence. So, in that's why I have written that, and that's why I put that bracket.
conditionally independent doesn't imply
Definitely not. Independence imply, but conditional does not. The right to left you can go actually, but left to right you cannot. Conditional is a relaxed, more strict kind of, sorry, not more strict, relaxed, yeah. Okay, so this is conditional independence, and it might not be for 3 actually, it might be for n number of events also, okay. That given that 5 things has happened, the 6th and the 7th things are now conditionally independent. So that is also possible. Never, always try generalizing things to n number of variables, okay. It is not necessary that things are only for 2 or 3. So now, as I said earlier, that independence is extremely important in machine learning, and let us try to understand why, okay, because we will be using it many times. So, importance of statistical independence. Okay. So, let us take 2 events. Let us think of some example. Okay. Let us say I am taking an event where I am drawing a card from a deck of cards and I am throwing a dice. Joint event, right? Event A is drawing a card from a deck of cards which has 52 cards, and event B is throwing a dice. So, how many events are there in A? 52, right? How many are there in B? 6. So, the joint probability table, how many entries will be there? 52 times 6, because we create that table, right? So, consider A to be drawing a card from a deck, okay. So, and B is throwing dice, okay. So, B is just throwing a dice, which is simple one. A is drawing a card from a deck of 52 cards. So, in that case, A, it will take values A1, A2, A52. Okay. You can think of A1 to be, let us say, red spade, A2 can be black spade, and you can think of it like that, right? 8 of clubs, 7 of diamonds, like that you can think of 52 events, okay. And B is, we will have 6. So, it is like getting a 1, getting a 2, getting a 3, getting a 6, okay. So, probability of A equal to AI, comma B equal to Bj will have 52 times 6 entries. We agree, right? Because I can take 1 to 52, J can take 1 to 6. So, 52 multiplied by 6. So, that many entries this can have. Now, what is the learning problem? Let us try to understand. Now, we assume that the dice is unbiased. That is the assumption. We assume that each card will have an equal probability, might not be. The one who is having the card might be a magician or something, and he might always make you take some card, right? You don't know that. So a machine learning problem or a learning problem, not even machine learning, talk about learning problem. A learning problem in this context can be that you perform these experiments A and B k number of times, you will have observations, right? And based on that observations, you will like to find out the probability. Because the probability we are assuming till now, but we will not have that. So the learning problem in this context will be to find out the entries of these probabilities, right? So I am using the term statistical learning, which has a very close relation with machine learning. Our objective is to infer probability B equal to Bj. Let us call it what? Let us call it mu ij maybe, okay, for all I and j given data. I have some data and the data might look like, I don't know, let us say I am just randomly creating some data, let us say. So A10, B5 can be first data, A18, B1 can be my second data, third data can be A10, B6, fourth data can be A45, B3, and you can have data like that, right. So you have performed the experiments many times and these are the observations you have. So this is the data you have, okay, and from this data you want to find out that mu ij. That is a learning problem, okay, correct. So now can you tell me how many parameters, mu ij I will call as parameter. So whatever I want to learn is known as parameter, okay. So how many independent parameters do I need to compute? How many independent parameters are there? So can you tell me number of independent, not statistically independent, but yeah, parameters? So how many parameters do you need to infer from this data? 52. 58. How? If you are doing 52 plus 6, I know that, but why are you doing a product? 52 into 6 minus 1, why? Should be equal to 1. So total number of parameters, think of the table, how many entries are there? 52 into 6. So that is the number of unknowns. But you have one constraint, that summation of that should be equal to 1. So you only need to find out 52 into 6 minus 1. Because if you find out those, you will just subtract from 1 and get the last one. So number of unknown parameters is 52 multiplied by 6 minus 1. Which is, I will say, quite a big number. What, 311 or something like that is coming, I think, but yeah. Okay. So this is the number of parameters that we will have to deal with if there is no assumption, right? But now, suppose these two are independent, which actually they are, okay? Because I have taken the examples in that, I mean, I have set the example in. So if they are independent, then how many independent parameters are there? 56. How?
51 for the cards.
Correct. Because 52 for the cards minus 1, because and 6 for the dice minus 1. So 51 plus 5, which is 56. So by just considering them to be independent, I have reduced 311 to 56. And this is a small number we are dealing with. Just imagine if there was actually billion or something like that, you could have reduced it to few thousand potentially, which means huge computational gain can be achieved by this independence assumption. So if A and B are independent, then number of parameters in independent parameters obviously.
What do you mean by independent parameters?
I mean those you definitely need to find.
So what does the mean independent here?
Here independent means that these are the basic parameters. If you find these parameters, the other parameters you can find deterministically using these parameters. Because the summation is 1, so you can find them deterministically. So it is not statistical independence as I said, it can be, but I am talking about that if you find everything else, this is just a function of those things. Okay. So this will be equal to, as I said, 52 minus 1 plus 6 minus 1, which is equal to 56. So it is like if you know what is the probability of getting a head, then probability of tail you don't need to find out. It is 1 minus that. If you know what is the probability of getting 1, 2, 3, 4, 5, then probability of 6 is known to you because this is 1 minus the summation of the other things. Right? So in that sense. So this is the reason we are interested in independence. This is the reason machine learning researchers really love independence. Okay? And this is the reason. Okay. Okay. So now maybe I should introduce the most important law now, rule, but that is basically a application of the sum and product rule. So the most important thing, so you will realize that the course is called probabilistic machine learning. So we will do probabilistic machine learning, but for most part of it we will be doing Bayesian machine learning. And the name Bayesian comes from Bayes' law. I guess all of you know about Bayes' law, but just for completeness, let me introduce it here. So probability of A given B is equal to probability of A, probability of B given A divided by summation over A, probability of A given A. Okay? And you don't need to remember this because this is just, you can easily get it just by repeatedly applying the sum and product law. It is 3 or 4 times applications. How? So if I have to look at the proof, it's like a small proof actually. So first I want to find this. First I will use the product law in reverse. What is the product law? AB is equal to B multiplied by A given B. So if I use it in reverse, it will be AB by B, right? I will again use the product law on the numerator. And what will it give me? Probability of A, probability of B given A. On the denominator, I will use the sum law. So B is equal to summation over A, AB. Right? And lastly, I will use the product law on the denominator, and that will give me the result. So which is equal to A, B given A divided by summation over A, probability of A, probability of B given A. So I just applied product law and sum rule 2 or 3 times and I arrived at that. So those are the fundamental things. This is just a byproduct. Okay? This is just a byproduct. So in our case, remember I told you that B will be generally my data. In the machine learning context, B will become my data. A will become the parameter I want to infer. And the right hand side will remain as it is. We will not use the Bayes' law in this form. We will actually use the Bayes' law in, okay. So in numerator we will be using this, in denominator we will be using this. So that is the form we will be using throughout this course. Okay. So just to write it, so in our terminology that we will be using throughout this course, I will be using this terminology. Theta okay, and there are names. The first term is known as prior. So I am just quickly introducing these things. We will have long lectures on those things later. The second term is called likelihood or data likelihood, and the denominator is called evidence. Okay. Why is it called prior? It is called prior because it is probability of theta before you have observed any data. So it is like what is your prior belief about theta. The likelihood because it is probability of d given theta. So how likely it is to observe the data for a given theta. Okay, we will talk about it later in more details. And that d is your data, that is your evidence. So that is probability of d is your evidence. So that is why this name are used. Okay. So prior times likelihood divided by evidence. Evidence is generally not used until and unless you are doing a model selection problem, which we probably will do at some stage. So generally we will realize that what we will use is actually a proportional form, prior times likelihood. And the left hand side, this has a name, this is known as posterior. This is posterior because this is your belief about theta after you have observed the data. So the names are quite obvious. Okay. Any doubt? Questions? No? Okay. So yeah, so this is the thing, prior, likelihood and posterior. Now I have some time, let me quickly introduce the random variable and probability distribution. Okay. And then I will just introduce one more thing and we will stop. Random variable. What do you mean by random variable? What is, because till now we are talking about random event, outcome of a random event or random experiment. So we are using the term event and experiments. This is for the first time I am using the term variable. So what do you mean by random variable? Anyone?
Function from sample space to
Yeah. Tell, you are right.
function from sample space.
Right. It is a function that maps from the sample space to the real space.
Having some properties.
Yeah, obviously. Okay. A simple example is in tossing a coin. What are the outcomes? Head and tail. That is my sample space. I can define a random variable x, which I can say that will take the value 1 if it is head and 0 if it is tail. So what I am doing is I am mapping head to 1, tail to 0, and that is what random variable is. So it takes a event and maps it to some real number, and each real number will be associated with a probability obviously. Why is it done? Because at the end of the day you will like to write a computer program. How will you write head and make computer understand head? It can understand numbers. So if you have to do maths, you need things in numbers. So that is the only reason. Okay, there is no, I don't see there is any other reason. There is another reason actually. We will soon talk about distribution, and those distributions will only hold if there is a variable. You cannot define a distribution mathematically without having a number, because the distribution will need to satisfy certain property which you can only calculate if that is in numbers. Okay. So this is the main reason. For me, the main reason is that I have to write a computer code, because I am talking from a machine learning point of view, and I can only do it if I have numbers. Even in natural language processing, it's a language, but I have to convert it to numbers, vectors. Otherwise, I cannot do NLP. So same kind of thing. Okay. So random variables maps from event space to real. So this is real notation for real. Okay. So yeah. bold phasor. So that is a notation to real space. So let me write real actually. Example, in tossing a coin, my sample space is head and tail.
So the main reason for introducing random variable is
Is to do mathematics with it. You can think of it like that. Like this, yeah.
some books say that to introduce the features or to make the task simpler,
Same thing, right? So that's what, to do mathematics. That is simple. Features you said, right? Features is the input to machine learning, right? So I said mathematics, which is simpler, right? Otherwise, it will be very difficult for you to follow. Think of a distribution, right? Bernoulli distribution that only follows when you write 0 and 1. If you change -1 and 1, that whole expression changes. So without doing that, how can you come up with some standardized expression? So it is more about standardization and all those things from a mathematical point of view. I am speaking from a machine learning point of view. For me, it is to write computer program. So I'm not from the book point of view, because book you are talking about a statistical book. So they will talk from statistical correctiveness. I will talk from machine learning point of view. And for me, it is so that I can use those numbers and write codes, right? And to do maths simply. Okay. Head and tail. So we can define a variable, which is a random variable, x, such that x is equal to 1 if e is equal to head is 0 elsewhere. Okay. Now you will ask that why 1 and 0? Yeah, you are free to take it 10 and 13. But then when you try to write the distribution, it will not be standard. You have to come up with your own distribution. So 1 and 0, because I will later try to use some distribution which takes this value. That is the only reason. Okay. Okay. And how do you define a random variable? A random variable is defined by a probability measure. There, like each of these events is associated with a probability, and generally we associate a function with a random variable. That function is known as either probability mass function or probability density function. Okay. Some books, or I will say it is a thought process, a school of thinking is that PDF is not fundamental, they call CDF is fundamental, and from there you come to PDF. And there is another school of thought which will say PDF is fundamental, you go from PDF to CDF. Okay. So that's a school of thought. The reason of going from CDF to PDF is that you just need to take a derivative, and we know that all functions are differentiable. Whereas if you want to go from PDF to CDF, you need to integrate, and that might be difficult. Some things are not integrable. So that is the reason, that school of thought, but I am fine either ways. Okay, we will be mostly working with PDF, so I will go with that. So yeah, so before I go to PDF and PMF and CDF, random variable is of two types. One is discrete, other is continuous. Okay. Discrete means the variable will take discrete value, 0 and 1 for example, and that discrete may be countable, may be uncountable. So I mean countably infinite, I mean not uncountable. So the number may be countably infinite also. One example is Poisson's distribution, which is a discrete distribution, PMF, but it can take countably infinite numbers like 0, 1, dot, 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 infinite. It will not take a fraction, but it will go up to infinite. Okay. So both of this comes under discrete. Okay. As long as it is countable, it comes under discrete. Continuous means it can take any value. Example of discrete is tossing a coin, throwing a dice, drawing a card from a deck. So all the examples I was giving were discrete. Continuous is, let's say, what is the distribution of your height and weight in the class. Now that's a continuous value. Okay. So example is tossing a coin, let's say. And here example is height of students. So if you try to find the distribution of that will be continuous. Height can be in fractions and can take any values, and so on and so forth. Okay. Obviously, you can always convert a continuous to discrete. You just create classes Like instead of measuring height, you say short, medium, tall. Now it becomes discrete. So that you can always do, not preferred, but you can do. Okay. And discrete random variable is defined by a PMF. Random variable is defined using PMF, which is probability mass function, PMF. Okay. And what is a PMF? First of all, it is a function, because the name itself has function. But it is not just any function, it is a function that satisfies certain properties, two properties to be specific. So, a function f x x, this is how it is denoted, okay, where this capital X is your random variable, small x is the outcome of a or realization of that random variable. Okay. Realization I said earlier, so that is basically outcome. Okay. Like if x is tossing a coin, so capital X, so it small x will be either 1 or 0. So it is small x is the value that capital X can take. So a function f x is a PMF if number 1 is f x x is between 0 and 1. This means that 0 less than equal to f x, x less than equal to 1. This is what it means. Okay. And the second condition is summation is equal to 1. Okay. I think most of you know about it. Okay. So this is the PMF. PMF is there for discrete random variable. For continuous random variable, we have the PDF. And similarly, if I go to PDF, probability density function. Don't use, I mean, sometimes people confuse probability density function with probability distribution. So if you see in some books they are mentioning probability distribution function, that generally refers to CDF, because distribution generally refers to CDF. PDF, the D has to be density. Okay? It is not distribution, it is density. And again, I am not writing it, the first statement, but it also has two conditions. The first one is that f x x should be greater than equal to 0, and the second one is integration minus infinite to infinite continuous. So now you see dx will be equal to 1. Okay. So this tells us one thing. I am not saying that f x x will be between 0 and 1. It can be more than 1, which means f x x is not denoting probability. It is just the density. Okay. And but f x x in case of PMF is denoting probability. So when you refer to mass, that is the probability, density is not. And density I am coming. So think about normal, what is the relation between density and mass? You integrate density to get, I mean, density times volume is equal to mass. So you have to integrate it in some manner. So when you integrate it, you get the probability. Density is intensity of an event. So it talks about intensity, relative intensity of an event occurring or not occurring, but it is not the probability. So someone having a mode density, so CDF of that is, that is the mode. So if you draw samples, more samples will be placed there. Okay. So it is talking about the relative, in the relative aspect, but not, okay. So, and CDF, this I think we will not need that much in this course, but just for completeness, I will mention it. This is how you denote it, capital F this is equal to minus infinite to small x f(x(x) dx, which is basically nothing but you can okay. And you can now see that now the probability definition is coming when you are integrating. If you are not integrating, then the probability definition does not come. And this definition tells us that for a continuous variable, the probability of taking a given number is equal to 0. Now, can you tell me why? Obviously, from this integration you can tell me, because it is lower and upper limit will become same, but from a, let us say, intuition point of view. Remember, because it is continuous, it can take infinite number of values. So, n is very large, and when you say something divided by very large number, you can think of intuitively that going to 0. Okay, so that is from intuition. Actually, the integration will anyways give you 0. No, there is no other. That's all. I mean, it is not, there is, it will never take a single value. Its probability is very less. Like if you repeat experiment because it's continuous, that single value will not come. Okay, it always takes strip. Just to, so some examples. Okay, examples later, maybe some statistics, let me define quickly. So, one is expectation. It is denoted as integration x dx. Okay. Expectation is the mean. You can think, you can relate it with average, that we generally do. You can relate those things with it. But remember, there is a probability sense here, so that is important. But a more generic term is the moment. Okay. And moment is defined as statistical moment. Moments is denoted as integration x minus xc to the power alpha f(x(x) dx. Okay. And you can now see a special case is if alpha is equal to 1, xc equal to 0, you get your mean. So, if alpha is equal to 1, xc is equal to 0, this reduces to expectation. Another special case is that if xc, if alpha is equal to 2, xc is equal to mu, or which is the expectation, then you get your variance. Okay. So, variance is a measure of second moment. There can be other measures also of second moment if you change the value of xc. Okay. Like putting xc equal to 0, that is another measure of second moment, and in that sense. There is also higher order moments. Third order moment is known as skewness, fourth order is kurtosis, and you can have it like that. So, alpha is the one that controls the order of moment. So, the value of alpha is the order of the moment. Alpha 3 is equal to third order moment, alpha 4 is equal to fourth order moment. Okay. Lastly, for today, I will quickly give you, obviously I could not finish everything, I was expecting that I will not be able to. So, we will finish it on Monday before we start with other things. But just to give you some examples of distribution, popular PDFs and PMFs. So, there is Bernoulli, there is binomial, there is multinomally, there is multinomial. Okay. Then there is Gaussian, obviously normal. There is Poisson. Poisson you will not need in this course, so I am not writing it, but Poisson is obviously there. Then there is beta, there is gamma, there is Weibull, and there are Cauchy, and there are so many others. I can keep on writing, this page will not be enough probably. But you do not need to remember all of these things. Like each of this distribution will have certain properties, will have a PDF or PMF, they will satisfy certain things. You do not need to remember any of that. you just should know that this distribution exists, and whenever needed you go to Wikipedia or open Google and check it out. Okay. I think there is no point in remembering them when the internet is available to us. For example, in the exam if I give you some distribution, I will not expect you to remember those. I will give you the formula and all those things, and the idea is you might have to operate on it but not remember it. Okay. So, all these distributions, many of these I covered last time, I will not cover this time. They are there in chapter 2 of Bishop as well, the main book. So, you can refer to that book if you want, you can read it from last year's video, last year notes and all those things, but we are not covering it this time around. I think even in this year's notes it is there, but we will not cover it. What I will do, I will cover is the joint distribution is I have already covered. So, I will just cover the Gaussian next time, univariate and multivariate, because that is the one we will need repeatedly. And we will, let me quickly introduce it in 1 minute, but I will again cover it next time, which is the distance metric. Very quickly let me introduce it. So, see, if I give you two distributions and if I ask you are these two distributions same or identical or not, how will you find it out? So, you need some metric. So, there are many metrics, the most popular one is scale divergence, okay, which is the Kullback-Leibler divergence. Kullback-Leibler divergence, okay. And how do you write it? KL, P is my one distribution, Q is my let us say other distribution. This is denoted as integration Px log Px by Qx dx. You can write the opposite one as well, Q and P, just you need to change Q and P. So, Q log Q and P dx, and the important point to note here is that they are not same. So, this is a distance metric that is not symmetric, which is unusual. It is like the distance from me to you is not equal to you to me, which is not intuitive, but it is what it is. Okay. This is the most common one. The other thing is that this quantity is always greater than or equal to 0. I will probably give you to ask you to prove it at some point, but this cannot take negative value, it can be proved, okay. And it will be 0 when P is equal to Q, because you will get log 1 and that will make it 0. So, this quantity is equal to 0 when P and Q are same, and the lesser the distance, the lower this number, okay. So, that is, so we will cover this thing again next time, okay. Thank you.